All right, let's go ahead and get started. So today's going to be fairly quick. We're just going to finish up with mass spec. I'm going to hand you out the NMRs from the demo that we did the other day, so we can see whether or not we actually did make 2-octanol or not. I've got to catch a flight here in just a minute, so we're going to be relatively quick. So the last thing that we need to talk about is mass spectrometry. I do not care that you know a whole lot about mass spectrometry at this point, other than it's important. Okay, I mean, it's a complicated procedure. We don't have enough time to go into a lot of stuff, but it's really powerful. For those of you who are going to go into medical school and may do research at some point in med school, you will use mass spectrometry. It is one of the most sensitive techniques we have to detect molecules. And basically, as the name says, it's dependent on the mass of a molecule. Actually, it's dependent on its mass to charge ratio, which is another topic for another day, but that's what M over Z is. The convenient thing is that quite frequently the charge on the molecule that they put on there is typically 1. And if it's M over Z and Z is 1, then M over Z is equal to the molecular mass. Okay, so that works out pretty well. What you need to know is that here's an example of ethylbenzene. This is what the mass spectrum looks like. You can see the positively charged ion at 106. That is the molecular ion for the intact molecule, but you'll notice there are peaks that are lower in mass. That's because if we remove an electron from this molecule to make it positively charged, does everything have an octet? No. And so is it stable? No. And it will decompose into things that are more stable. And hence that is why the base peak, which is always the tallest peak in the spectrum, is the most stable species. Okay? So this has lost a methyl group, and now you have this CH2 with the positive charge on it. That is the base peak because this is now in that positive charge is in resonance with the benzene ring. This is a fingerprint of this molecule. Okay? This is something that might be a little more of interest to you for a variety of reasons. Hopefully not. All right, but if you are interested in forensics, they love mass spectrometry because mass spectrometry can detect tiny, tiny quantities. Femtomolar, picomolar, essentially a drop of something in like Lake Michigan kind of detection, okay? I mean, not literally, but you get the idea. It's huge. So when they wipe down a car to test for drugs, they're going to go use mass spectrometry because people can clean and vacuum and all kinds of stuff. You can't get it clean enough to beat mass spec. So this is cocaine. It has a molecular weight of 303. But how many things have a molecular weight of 303? Not just cocaine, right? So if you are a forensic scientist and you're on the stand at a trial and the prosecutor asks you, well, what was the molecular weight? You go 303. The jury's not going to believe you. They're going to go, because the defense lawyer's going to come up and go, and so do 1,000 other molecules. My client didn't have cocaine. He had one of these other things in his car. Surprise, surprise, right? But the fingerprint is this what we call fragmentation pattern. This is if you remove an electron from cocaine, but then it decomposes into these fragments. And only cocaine decomposes into these fragments. And so what they do is they take the spectrum that they get, from the crime scene, if you will, and they compare it to a database of known compounds. And if they match, you got them, right? If this peak isn't there, if that peak's not there, that peak, that peak, that peak, that peak, that peak, all these things, if it's not there, it ain't cocaine, okay? And so that can get you either in an orange jumpsuit, or it can get you free, right? One of the two, all right? So, what is mass spectrometry? Mass spec is the analysis of molecules and their molecular fragments based on their mass to charge ratio. What kind of information can you get? Well, essentially all you really get is the mass to charge ratio, and you get fragment ions, and you can get their intensities. That's basically all you can get out of the technique. However, if you're clever, you can do a lot of different things with that information to get a lot of structural information from it. Okay, so there are a lot of mass spec techniques available these days. They're so-called EI, or electron ionization. It's what you saw for the cocaine example before. There's chemical ionization, there's electrospray ionization, there's matrix-assisted laser desorption ionization, there's fast atom bombardment. There is a ton of things that we can do these days. The cool thing about these that I have highlighted, these are the instruments that we have here on this floor. They allow us to detect large biomolecules quite easily. They have huge masses. I mean, biomolecules have huge masses, and so we can detect them with these techniques quite easily. Up until about the 1980s, people thought mass spectrometry was kind of dead, because the tough part about it is that mass spec, you have to get your molecule into the gas phase, and that kind of limited it to small organic molecules that could boil. Has anybody ever seen a biomolecule boil? No, right? So we needed additional techniques, and when those came in the late 80s, that really reopened mass spectrometry. This technique is over 100 years old. So why should you care about mass spectrometry? You're going to care about this for a variety of reasons, right? If you're interested in pharmacology, medicine, or forensics, or environmental science, you're going to do something with mass spec. Again, it can detect things extremely dilute. If you're interested in biology, you're going to be using mass spec at some point if you go into research. We can detect trace drugs quite easily in human serum, human excrement, human urine, whatever, very easily. And so pharmaceutical companies use this all the time to figure this out. But more importantly, you might be interested in it for these 4 little dollar signs that I have shown here. I did a lot of mass spectrometry work at Vanderbilt. When I was there, I worked with a lot of mass spectrometrists. During the ups and downs of the economy, none of my friends ever lost their job. And they were working in industries that laid off a lot of people. Because this is the one technique that is today considered so essential in these industries. That if you get the experience, you get the expertise, you will land a 6-figure job right out of graduate school. Okay? And you will probably be able to keep that job through good times and bad. Okay? It is a essential technique these days in the molecular sciences. The way that this works, more or less, again, this is kind of a crude drawing of this. This is for electron ionization, which is the oldest of the techniques. You have a molecule that comes through here in the gas phase, so you have to boil it somehow. One way to do that is to run the molecule through a gas chromatograph. Have you all done GC yet? Yeah, so you're boiling stuff. It comes out the end of the GC. Why don't you just stick that into the mass spectrometer and you can do this. So you've got your gas sample coming through. You've got a what we call a source, which creates an electron beam. That electron beam has a wave function, right? And it will interact with the molecule and kick out an electron from the molecule to give it a positive charge. Some people call this electron impact mass spectrometry. That is actually not correct. It is electron ionization. So if you see impact in your reading or whatever, know that they're wrong, okay? So then it's positively charged. We accelerate it through these slits, right? So we got something that's positively charged. You make these slits negatively charged. It attracts the ion towards it. And as it's traveling towards these targets, they actually put a little slit in there. So most of the molecule actually hits the target, but some of them pass right through. And those small number that pass through end up going through what's called an analyzer. In this case, they're showing a magnetic sector. What happens when we have something that's charged and it's moving? What does it generate? It's a magnet, right? So what happens when two magnets come into contact with one another? They can either attract or repel, right? And they will move. And so it turns out that as these molecules come through, they're charged, they have a magnetic field, and they will bend as they go through the magnetic field. They'll either get attracted to the North Pole or the South Pole or whatever, right? And they'll move. And they move based on how heavy they are. And so where the detector is, we just figure out how far they move. We can figure out how far they moved. We know what their mass is, and we can look at that data out on a computer, and we can see things that look like the mass spectra we just saw, okay? So again, that's not impact, that's ionization, electron ionization. This came from the internet. But basically, you've got your inlet. This comes from a gas chromatograph, and again, you can repel those ions because you have a positive plate here. They're positively charged, they get repelled, they get attracted, kind of go through the hole and on to the analyzer. So that's really all I want you to know about mass spec. Keep it kind of simple. want you all to take a look at the NMR. So this is an NMR spectrum from the sample that we had the other day when we did the oxymercuration, demercuration, right? And I told you that we were going to get what kind of alcohol? Morkovnikov alcohol. And you all believed me, because I told you, right? You shouldn't believe me. You should look at the data. And the data seems to support that. I want you to look at this NMR spectrum and tell me how come the data seems to support that. So when you're looking at this spectrum, oh, you got it. When you look at the spectrum, you can see that I've drawn the molecule up here, the 2-octanol. What is going to be telling in that molecule? What do we need to be looking for? What's going to be diagnostic? The OH is important, but the OH can exchange out on us. So it's going to be hard. And even if it's 1-octanol or 2-octanol, that OH is going to be more or less the same, right? Well, what we can notice is this proton right here is going to be the furthest downfield. Will everybody agree with that? Okay. And it's going to have a neighboring CH3 and then 2 hydrogens on the neighboring CH2. Right? So it's going to be a multiplet. It's going to be downfield. What's going to be the splitting for this methyl group? How many neighbors does it have? So it's going to be a doublet. So I should see a doublet for something that integrates to close to 3. I should see a multiplet for this. And all of these are going to be hard to tell because they're going to be all bunched together right there. Okay? But if I look at this in the blow-up, somewhere around 3.8, I've got a multiplet. And at about 1.2, I've got a doublet that integrates to more or less 3. And at 0.9, I've got a triplet that integrates to about 3. Where did I get that triplet? That's at about 0.9 ppm. It's this one.
Yeah.
So that's CH3. Right? So that is a triplet that appears at about 0.9. That is a doublet that appears at about 1.2. And so clearly we made the Morkovnikov alcohol. You would not have been able to determine that easily by IR. You would not have been able to determine that easily by TLC. You might have been able to determine it by GC if you had the standards, right? But here we don't have any standards, we have raw data, and we're able to determine that we have the Morkovnikov alcohol product produced quite easily. Any questions about any of that?
Can you explain why CH3 right there is triplet?
How many neighbors does it have? How many neighboring protons? It's got these 2, right? And it's the furthest away from the alcohol, so it's going to be the furthest upfield. That's why it's at 0.9. And it's got 2 neighbors, so it's going to be a triplet.
So we don't look at the H's attached.
All the hydrogens are important, but you can't really interpret these very well because they're all this big set of blobs that are right there. They all have very similar chemical shifts, and they all start to overlap, and so it's a force of force, which is a lot of.
Which carbon did you say was the triplet?
I didn't say carbon was a triplet.
Or I mean,
Protons.
I'm bad.
This methyl group is a triplet.
Oh yeah, because of the 2. Okay.
This methyl group is a doublet.
Oh, okay, yeah.
When you're looking at neighbors, you're not necessarily looking at the position, you're looking at hydrogens, right?
You're always looking at the hydrogens and protons. Always. Is that pretty clear? I am not going to be here Friday, but you will be. And I have an assignment for you all to work on while I'm gone. It is a skills evaluation, okay? It is nothing for you to worry about. I'm ready just to take it, okay? You will not be allowed to work in groups, but you'll be allowed to use your notes in your book, okay? So Ms. Sharon will come in and hand that out. You'll have the entire 50 minutes to work on it. There are 4 questions. It should take you about 50 minutes to complete it, okay? Should take you about that long. So, pretty comprehensive. Covers just about everything we've talked about up to this point in terms of chemistry. Actual reactions. So, kind of get you ready for thinking about the upcoming test. It's kind of a freebie in a way. Gives you kind of an idea of some additional problems. Several of you have asked about additional problems in the past from me, and so give you a chance to have it. So, be able to work on that on Friday. Any questions?
Will that assignment be worth points?
It will not be worth any points. It's an evaluation. So what I'm going to do is I will evaluate it. I will get those back on Sunday, and I will make comments, and I will give that back to you. So it's free feedback, okay? It's a no-risk, free feedback kind of thing. It is in your interest to do the best that you can on it, though, okay? All right, have a good one.